Okay, excellent. Well, guys, it's good to have you here tonight. So with our meter class, you know, we couldn't have class last week. I was doing some traveling out of town. Hopefully you guys watched that video clip on relay testing and got some of that relay testing done. And we are, you know, kind of reaching the end of a lot of our content. We'll see how much we can get through tonight, because I do have some neat diagnostic case studies that I want to share with you that I think will do a great job of bridging that gap between multimeter diagnostics and scan tool diagnostics. But I want to make sure we first focus on the stuff you guys need to do to get your assignments done. Now, what I'm going to do first is I'm going to go to our class calendar. And when I do that, you'll see here we are. It's March 25th, right? We're getting to our last week of March. And you'll notice that there's nothing going on next week. And that is because next week is spring break for us here at ARC. So there is no school for us next week. And so I have no assignments or anything due. But if there's some stuff that maybe you didn't get done earlier that you're behind in, by all means, get that stuff done and get that stuff submitted. Maybe it just wasn't practical for you to get the video shot, or you had some type of technical issue, you know, use that week to catch up, so to speak. But we, you know, this is only a 1-unit class. We are kind of winding things down or wrapping things up, depending on how you look at it. The big things due for this week, of course, is our third little quiz. And one of the things that I'm really excited about is this RX-7 charging system diagnosis. So what I'm going to do is I'm going to click on this lab quiz sheet 3 so we can check it out. More meter knowledge. Okay. We'll click to this thing. We'll go ahead and open it up. Clear the drawings. All right. So this quiz is pretty straightforward. As you can see, it's only 5 questions here, and it's all about using your multimeter. Okay. Now, this is what I'd like you to do. You might get to something where you're like, hey, it talks about measuring capacitance. And maybe you look at your meter and you're like, oh, well, it doesn't look like this meter does capacitance. I read through the manual and I don't see capacitance on there. Here's what I want you to do. The Snap-on meter does have a whole section on capacitance, but just to show you another way to get this done, I'm going to clear this out, and I'm going to type into Google how to measure capacitance on a multimeter. Boom, there we go. And remember that Fluke is like an industry standard in multimeters, right? Fluke are the meters that usually have the yellow covering on them. That's an industry standard, so that's a good, reliable source. The one thing I will say is if you're just searching for stuff off the internet, don't go to, you know, Jim Bob's lesson of how to, you know, do something with your meter. Always go with reliable sources, right? So I'm going to click on that thing, and it says good capacitor stored electrical charge and may remain energized hours after power is removed. In fact, what is a capacitor? Well, it shows us number 3. That little symbol right there is how you measure capacitance, and it goes on to describe it. Turn the dial to capacitance measurement mode, which looks like that symbol. Actually, here's another thing around the dial of a Fluke meter. And if we look at this, there's that symbol again, number 13. Oh yeah, that is how to measure, that's for capacitance. So let me draw that symbol real quick. It looks like one line, and then it's got almost like a C and another line, right? There it is right there. And there's my drawing. Okay, so what is a capacitor? A capacitor, also in automotive terms, we call these condensers in our old ignition systems. So a capacitor or a condenser, guys, a capacitor or a condenser, what these basically act as like is a fast acting battery. It can be quickly charged or discharged. A-R-G-E-D. So it can be quickly charged or discharged, and it's typically used out as a filter, but it can also be used as part of a timer circuit or a number of other things. So if I take my drawing tool, basically if I hook this thing up to a battery, okay, what would happen is I would stack, you know, electrons on one side and positive ions on the other side, and within milliseconds, this thing would be charged and it would match the battery's voltage. So if this was a 12-volt battery, if I hooked up the capacitor 12-volt battery, within, you know, a very short period of time, boom, it's going to be charged up. Then if the battery voltage were to drop, let's say I would turn on an electrical load or something, and the battery dropped down to, let's say, 11 volts, well, now the capacitor is sitting here at 12, and so he will quickly discharge and fill the battery back up, okay? So capacitors are used when you need, you know, when you need to charge something or discharge something really, really fast. That's the perfect time for a capacitor, okay? They can charge more quickly than a conventional battery, and they can discharge more quickly, okay? So we'll use them all over the place when we have something that has maybe a varying voltage level, and we want to filter out some electrical noise from that, okay? A lot of times people will, maybe they put in some high-end stereo system in their car with a big amplifier, and that thing is pumping 100 amps to a couple of big subwoofers or something. Well, when that thing starts cranking up the sound, it's going to lower the battery's voltage in your car, and it might make the car run weird. And what people will do is they will put on, I'm going to search up a car stereo. Lightning cap, they'll put these big capacitors on here that kind of looks like a weird tubular battery, but it's a big capacitor. And what happens is as your battery's voltage drops, it helps charge the battery back up. And then when the battery's voltage is high, it can instantly charge the capacitor back up. And it acts like a big shock absorber, if you will, to the electrical system in your car. So if you were going to put a big car stereo amplifier in there and a bunch of speakers, what you notice is you'd have more pop from your speakers, more sound out of that thing if you had some of these capacitors in there, kind of helping absorb that shock to the electrical system. So capacitors, fast-acting batteries, there's actually a way for us to measure their capacitance, which is measured in farads or microfarads, and some of your high-end multimeters have the ability to do that directly. In the case of a fluke meter, if it has this little symbol in there, what that means is you can put it on that setting, hook up the leads to the capacitor, and measure its capacitance. All right, pulling this all back to our quiz, you can see that if I look at all the symbols, oh, okay, D is the right answer for this question. Another way that you can answer this question is you could go, okay, well, that's microamps, milliamps, and regular amps. Well, I know it's not either one of those three, so it's got to be this one, right? So the other way you could answer these questions, and I'll use a combination of both, is process of elimination, okay? One of my jobs I look at as your automotive instructor is to teach you how to be a good test taker, because if you guys want to get ASE certified yourselves, that means that you have to be able to pass those ASE certification tests. And that means that you got to get good at taking tests, right? So I just wanted to kind of share that with you. So one of your things that's due this week is to take this test and do the best job you can on it. Remember, use process of elimination, find the answer that's most correct, right? Let's see, what I want exact voltage measurements. So would I want a jumper wire? No. Would I want a non-powered test light, fuse jumper wires? No, I got to find the best answer for each question. Remember, with technician A and B questions, what you guys want to do is select the guy that's most correct, or both of them. And the way I do that is I split it up into two true false statements. So I say student A says the meter lead should be connected in parallel. I would ask myself, is that true or is that false, right? Technician B says that the meter lead should be connected in series. So both of these guys cannot be correct. It's either going to be A or it's going to be B. And so I'll let you guys figure out what that is. When you get this thing all done, I'll just click stuff here at random. I'm going to click submit. And when you see the confetti pop up on your screen, you've finished the test. Now I got 3 out of 5, and it'll give me a little bit of review there. So one of the things we have to do this week, that'll be due at the end of the day tomorrow, is to take that little 5-question quiz. I look at that's pretty easy. And notice when I took that quiz, now there's a line through it because it shows that I've submitted it. All right. Okay. So the question is we're going to measure current flow. Do we do that in series or parallel? Well, remember, if you're measuring current flow with your meter, you have to put your meter in series with your circuit. Okay. So what that means is if I want to measure amps, not only do I have to turn the knob over to measuring amps, I have to select the right setting there, but I got to move the meter lead. And then I got to put the meter in series with the circuit so that the electrons flow through one meter lead, flow through the meter so it can actually measure how many electrons are going through it, and then going through the other lead. Okay. So when you're doing amps, when your meter is kind of in a vulnerable state, and that is measuring those amps in series. And remember that most of these meters can only have a maximum of 10 amps flow through them, okay? Unless you're using some type of amp probe or something. But if you're hooking the meter up directly to the circuit, it's hooked up in series, and you really got to be careful to not flow too many amps through it. Otherwise, you'll blow the meter. Now, a good example where I have you guys testing some current flows is actually in the horn activity that we did. Actually, you guys didn't do the whole horn activity. You did part 1, right? When we come back from spring break, there'll be a part 2. So here's what I'll say is if you go here to, let's clear out those drawings. Let's go back to our course. And last week I had a video that I put out for you guys. This video right here. So if you watch this video, at the end of it, we're back in the shop. I do use my meter to measure the amps through the horn circuit. And I've moved the meter lead over, and I basically put that meter, in series and hook it up directly to the horns themselves. And so I actually measure the current flowing through that horn circuit. Another thing I could have done in this, to measure the current flowing through my horns, and we'll see what the current flow here was. I can see the screen change real quick.
think it was 4.9.
Yeah, you should get 4.9. And when I do that, it'll actually make the horns honk.
Let's test out the horn.
Okay, so it's testing the horn. So let me draw for you how I hook this up, because you know what I realized watching this thing is you can't necessarily see the whole thing on there, right? So let's do this. I'm going to do a whiteboard here. And yeah. Okay, so here was the horn relay. And I took him out. And then there was a couple of pins sticking in that relay block. Okay. One pin basically went over to power. Okay. Now, how did I know that? I looked at the wiring diagram. Oh, that is not what I wanted to do. Let's try this again. So here is our horn relay. The switch circuit had 2 pins. One set of pins one pin went over here, and it went in parallel, and it went to a couple of horns. So here are my horns. And then from there, each horn had a connection to ground. Okay. The other pin basically went through a fuse, and it went to the positive battery terminal, or 12 volts. Okay. And what I did in the video is I took my meter. I will draw him bright green because our school meter is a bright green one here. I took my meter, and there's the screen, and I set him to measure amps. And I took one lead here of this guy, and I hooked it up there. And I took the other lead, and I hooked it up there. And then what happened is the horns honked. Why? Because current went through here, through the fuse, through my meter, to the other pin, and to the horns. The horns honked, they made noise, and because the current was flowing in series through my meter, I could measure it, and it measured 4.9 amps, right? Now, I could have done this another way too. I could have said, you know what? I'm going to plug the relay in here. So I plugged the relay into that spot. And what I then could do is I could have taken out the fuse for the horn. And so now I have a couple of terminals here where the fuse was. And I could have put my meter in right there. So here's my green meter. Remember, I'm going to set him to measure amps, and I'm going to take one lead, and one lead is going to go right here, and I would take the other lead, and the other lead would go there. And then when I hit the horn button on my, excuse me, allergies, springtime is here. Now, when I hit the horn button, the relay should activate, and the current would flow through my meter. So now I would have to hit the horn button inside the car. And then when I did that, current would flow through. It would flow in series through my meter. It would go through the relay to the horns, and the horns would honk. In either case, I would have to put my meter in series to measure the current flow. The only way one of these meters can measure current and without putting themselves in series with the circuit is to use one of these inductive amp clamps, where it clamps around the wire and measures the magnetism flowing around those wires and converts it into a reading that we can see. Okay. So hopefully that answered that question. And actually, maybe it's a little bit hard to see here. But that's kind of how I was hooking that up. In fact, it looked like it was so hard to get in there. What I did is I really cheated, guys. I put one meter lead on the positive battery terminal, and I put the other lead going straight down to the horn. So I bypassed the horn switch and everything else and went straight to powering those horns through my meter is what I did there to try to get everything to fit on the camera. Anyways, when you're measuring current flow with your meter, it has to be in series, and you really have to be careful and think about, well, what am I going to measure? Do I expect it to flow more than 10 amps? So in this case, I knew the horns wouldn't pull more than 5, so I was okay. If it was something like a fuel pump or something that would pull 8, this little cheapo meter only went to 5 amps. Something like a fuel pump typically won't exceed 10 amps, but something like a radiator fan, that will be 20 or 30 amps. So I could not use my meter for that. So you'd have to, you have to kind of know the circuit you're going to test and how many amps you expect it to use. Your other option is to make the investment in getting one of these low amps probes. Okay. It's kind of tough though, because the cheapest ones of these that you can find cost you about $100, and that's just how it is. And I also find that people get mixed up in the conversion between volts to amps, and we'll demo that in a bit. But it is a great way to go because you're not worried about blowing the fuse inside your meter. Okay. But, if you're just using a meter like this and you don't have one of these fancy low amps probes, you just have to think about, well, what am I trying to test? How many amps do we expect it to pull? If it's anything bigger than like a fuel pump, it's going to be pulling more than 10 amps. If it's something like a dome light or something small, that'll be less than 10 amps. But a radiator fan, the blower fan inside your car, a rear window defrogger, your headlights, all those things will pull more than 10 amps. And so that would blow the meter fuse. So you really got to watch that stuff. Remember, one of my tips that I shared with you guys a few weeks ago is you could put an inline fuse externally with your meter leads to try to protect that meter. That's another way to go. All right. So that kind of relates to one of the case study presentations I wanted to show you guys. So I am going to switch my screen share to that. And we're going to look at it because it is exactly what I was talking about. It's a kind of a different way to think about doing some diagnostics. And so I'm going to put this on presentation mode. We'll do the screen share a little bit better. And again, it's the horn circuit. Okay. So remember that how do you test a horn circuit? Any circuit for that matter. Really, your first step is getting familiar with the circuit by looking at the wiring diagram. I can't stress this enough. You got to get that wiring diagram so you know what you're up against. All right. So with that, here we have a little horn circuit. This is off of a GM vehicle, but most horn circuits are pretty similar, and that is why I picked the horn for one of our activities. Okay, so what do we have here? Well, we have power coming from a fuse, and then we got this horn relay behind the left side of the dash. Here's our horn up by the radiator on the car. And just like we've noticed before, that on our newer cars, we'll usually put a parallel circuit over here to the body control module so that the body control module can function this relay and then honk the horn. Because maybe you have a built-in car alarm or some type of key clicker functions, and you want the computer to be able to function the horn. That's how they do that there. So a quick one here is if the complaint was the horn doesn't work, but if you click the key fob and the horn honks, well, that tells you that, okay, the horn is good and the relay works and the fuse is good. And the problem has to be somewhere in my steering column through the slip ring or the clock spring in there or the horn switch on my steering wheel, something like that. Okay. So with the diagram in hand, you can figure out how the circuit works and you can quickly start eliminating things without even having to walk over and start testing the car really too much. So we have the diagram and I have, how would you test this? Well, you could test it just like I did in the video, and there's nothing wrong with that. However, I wanted to kind of show you a different way that you could test it when you really start to think about it. But this testing will require that you have a amp clamp and can measure the amps. So here's what I'm going to do. I'm going to zoom in on this a little bit. And now we're going to confirm the problem. The horn doesn't work. And we're going to attach our current probe here. Now, again, I want to show you how the current probe works. So I'm going to go to just my computer screen here. I'm going to share that. And now I'm going to kind of minimize this thing and fire up the good old document camera here, because I really want you guys to see how this thing goes together. And it doesn't matter if it's the low, kind of the low amps probe or the high amps probe. Let's get this thing going. Document camera, there it is. Okay. So both of these work the same way. And what you'll notice is that on the back of them, there's a spot to put in a little 9-volt battery. And one of my complaints is that, you know, you'll bump this switch and leave it on and put it in your toolbox and it'll kill the battery and you'll have to replace the battery. But that's just how it goes. All right. What this tool does, remember what this tool does is when you clamp him around a wire, he measures the magnetic field around the wire. In fact, if I open it up, you can see that there's a little arrow inside there, right? So if I clamp him around this wire, okay, as current flows through this wire, remember a magnetic field will generate around it, and this guy can pick it up, okay, with the sensor that's built in this tip here. Make sure it completely closes. If it's hanging open, it won't give a good reading. And actually, before I clamp it around the wire, what I need to do is hook it up to my meter, and I need to press the 0 button. So I zero it out, I clamp it around the wire, and then I pay attention to what settings I have this thing on. So let me zoom in on it. I'll try to refocus it here. So this guy, for every 100 milliamps he would measure, he will display or send to your multimeter 1 millivolt, okay? And on this setting, for every 10 milliamps he measures, he would send to the meter a reading of 1 millivolt. So it converts the magnetic field that it measures at the tip, it converts that into a voltage reading, and then based on what scale you have it set on, it would tell you basically how many amps are flowing through that wire, okay? So your meter is set to measure volts, and you have to be smart enough in your head to realize, hey, I'm actually measuring amps here because I'm using my current clamp. All right, and then different current clamps have different scales, right? So this other one goes up to 600 amps. So it's got a big old clamp on here because it's made to go around a big old fat battery cable. And the scale on this guy, if I zoom in on it, 1 millivolt, or I'm sorry, 1 amp equals 1 millivolt. So if my meter says, hey, you got 1 millivolt here, that really means there's 1 amp flowing around whatever cable you put it around. Okay. All right. So now that we've seen that, I'm going to switch this back to the computer, and then I'm then going to change my screen share back to our PowerPoint. And we'll go like this, and then we'll go like that, and we'll go like that. Okay, clean it up a little bit for us. So put on the low amps probe, and probably the easiest way you would do this is you could take the fuse out and put in a fuse jumper wire and put your amp clamp around that jumper wire to do that measurement. Okay. Now, okay, I lost the Elmo. Fine. I will just somehow, in the process of all that, I lost my mouse. There it goes. Okay. Close the program. All right. Yep. All right. So my document camera got upset, but I believe we're still rolling. Let me check my controls real quick and make sure I'm still sharing, and we are still, that looks okay, and we're still broadcasting. Yeah, okay, we're doing okay. Again, I've been having some computer issues, so I just want to make sure we're still rolling. All right. So imagine that we have this horn circuit. We've hooked up this low amps probe like this, and we go to push the horn button on the steering wheel, and we get this. We zero the probe. We pressed on the horn button, and we're going to get some different current flows. Okay, so here we go. Our first scenario is, we push on the button and we get no amps flowing. Okay, if we had no amps flowing at all, we got nothing. Well, that tells you something, right? Maybe the relay is unplugged, or it's totally defective, or I don't have a path to ground right here, but I have absolutely nothing flowing, right? So if I had no amps flowing at all, I'm looking at the relay. Maybe this fuse is blown out. I'm looking right here if I get past the relay, but I have no current flowing at all, right? Now, if I clear out those drawings, scenario 2, what if I push the horn button and now I get this, okay? So basically, what am I measuring here? I am measuring 15 milliamps here, and I'm looking for my current probe so I can see, well, what would that really be on the car? And where did the current probe go? Oh, here it is. So according to the scale on the current probe, if I was on the lower setting, if I was measuring basically 15 millivolts, that would be 150 milliamps. Okay, so I'm not only measuring 1 amp, but I am measuring some current flow. Okay, so basically what this is telling me right now is a little bit of current is flowing through this. It's being picked up by my probe. It's going through the fuse and it's going through the circuit. Now, a horn itself, the horn's going to flow somewhere between 4 to, let's say, maybe 6 amps. Okay. So I don't think the horn's actually working. But you know what's working? The control side of the relay. And so what this tells me is that I'm pushing the button here and it tells me that the fuse is good. So this is okay. In fact, I will just change my color. I'm going to give it a big green check mark. So it tells me that's okay. It tells me that the relay is plugged in and it's flowing through the control side of the relay. So that's okay. And it tells me that this is okay. So then my possibilities here for a problem are, oh, well, maybe the switch contacts of the relay aren't working. Maybe I have a bad horn, or maybe I have a bad ground circuit, but something basically on this side of the food chain is not working. Okay. Let me clear out those scribbles. Okay. Now, scenario 3, boom. Now I got a different deal. Okay. At this point, I am measuring a pretty considerable amount of current flow. This is enough current flow that, essentially I'm measuring like 14 amps right now. Okay. So at this point, what that would tell me is, okay, well, that means that this is working, that's working, this is switching. I most likely have a defective horn in this situation, right? So, the idea of using this low amps probe and thinking like, well, how much current does different things flow, is I could throw this low amps probe on there and pretty quickly get a direction to go on the circuit. Now, is that kind of overkill for a horn circuit? Yeah, it is, but we've been talking about horn circuits, and so it's a different way to do it, right? All right. So this would be a situation where maybe I have dead horns on the car. So anyways, I wanted to kind of demo that thing for you, show you how you'd use a low amps probe. I don't really use these low amps probes very often for testing horn circuits, but you know what I do like to use them for? Testing a fuel pump. Okay, they make it nice. And remember, let's say the horn was totally shorted out. I'm going to put my drawing tool back up, and let's say this horn was shorted out internally, and we had 20 amps that tried to flow through here. Well, remember, if my meter was hooked up in series, I would have just blown the fuse of my meter. Well, I could have 20 amps flowing through this wire. That's not going to damage this low amps probe, and it's not going to damage my meter either. So that's why I really like these low amps probes. You can also use them with oscilloscope. So if you want to graph out the current on an oscilloscope, you can do that. They're pretty sweet, but like I said, the cheapest ones you'll likely find are through AES Wave, and they're right around $100 or so. So they're not super cheap. But if you're doing a lot of electrical diagnostics, they are nice to have. All right. Let me clear out those drawings, and let's do a different scenario here. I'm going to do our no start diagnostic, and I will clear that out. And we will get this, we'll at least get this going part way through here. Okay, so let's see. we will get that going. And there we go. So we're going to take what we learned on the horn and using the low amps probe, we're going to apply it to a no start. So remember, when a car doesn't start, right, you have to first ask yourself, well, does it not start up because it doesn't crank? Or does it crank over, but yet it doesn't start? In this case, this vehicle cranks over, but it's a no start. But because it cranks, that tells me that the battery's got some voltage, the starter works, the engine's not frozen, right? So there's no point in me replacing the battery or replacing the starter motor typically if the car cranks. And I just want to make a point to spell that out for you guys, because I can't tell you how many times I've been by the local auto parts store, and I don't care if it's O'Reilly's or whatever, there'll be somebody in there and they're like, oh man, my car doesn't start. And what do they sell that guy? They sell him a battery or they sell him a starter because they're like, oh, it doesn't start. And it's like, well, dude, I can hear you cranking your car over out in the parking lot. I don't think it's the battery or the starter. You probably have no fuel pressure or a blown out ignition module or something like that. Okay. So this is a no start, but the vehicle does crank. And that is a very important thing to determine early on your diagnosis, because they're two different paths, right? Okay. So here we have a 2000 GM van. It cranks, but it's a no start. And of course, the question is, what should we test, why, and how? Now, I like to say every vehicle, every engine for that matter, needs three things to run, okay? It needs some heat. Now, heat, you think, well, what do we mean by heat? Well, where am I supposed to go? We need heat in the form of spark from our spark plugs, but we also need compression in our engine. So I'm going to put spark. So I need some spark at our spark plugs at the right time in the 4-stroke cycle. And I also need compression in the engine. So I don't care if I got the best split fire spark plug, double iridium, platinum 100 spark plugs, whatever, MSD wires. If the engine has no compression, hey, it's not going to run, right? So I have to have the right amount of heat. That means I have to spark at my spark plugs at the right time, and I have to have compression in the engine. But I also need some fuel, right? So I need some fuel. So this means that my fuel pump's running if it's an electric fuel pump, that the fuel injectors are getting a signal. If it's electronically fuel injected, they're turning on. I need to provide fuel for this engine, okay? And the last one is kind of a given, but I have seen some weird stuff. And that means that I need air entering the engine. And I've seen it where rats built a nest in the air box, and so the engine couldn't breathe in any air. I've seen it where the exhaust system was so plugged up, you couldn't move air through the motor, so it couldn't draw in any air because it couldn't get any exhaust out, and it was a no start, okay? So what does an engine need to run? It needs heat, it needs fuel, and it needs air, okay? With that knowledge, what should we test and why? Well, of these things, what's pretty easy to test? I like to go after fuel, right? I mean, as I crank it over, I listen to the way the engine sounds. If the engine has a good cranking rhythm, I go, okay, well, it seems like it's got compression. If the engine cranks and it sounds all weird, like then maybe I think, oh, maybe I got a compression problem, right? But if it cranks and sounds normal cranking, it has a good cranking rhythm. An easy thing that I do is I say, okay, well, I'm gonna give it some fuel here. So maybe I squirt some carburetor cleaner down the intake, okay? And I see, does it run for a second? If it does, it tells me the problem is fuel. If it doesn't, then I keep digging. Maybe I check for spark at the spark plugs, okay? But in this case, we give it a little squirt of carburetor cleaner, and it fires for just a split second. So we go, okay, aha, I have a fuel issue. So I'm going to put my fuel pressure gauge on there. And I know this is more than a multimeter, but remember the multimeter is one of the tools in your toolbox to figure out what the heck's going on. It's not the only tool. And this is why a master mechanic's going to have $20,000 to $30,000 worth of tools in his or her toolbox, right? So guess what? I have my fuel pressure gauge on there, and I have a big old fat no start, and I have no fuel pressure. Boom, I like this because usually fuel pressure ones are generally pretty easy to figure out, okay? So I don't have fuel pressure there. Well, maybe it's a bad fuel pump. Maybe it's a bad relay. One of my quick little tech tips is, because sometimes the fuel pump, remember it's an electric motor. Electric motors can stick and get stuck. I'll go back by the fuel tank and I'll beat on that fuel tank, okay? I don't know about you, but I like beating on stuff like fuel tanks and starters and different things, get some aggression out there. And a lot of times if you tap on that fuel pump, you can get it to be unstuck and it'll start up and run. And then, you know, oh, well, the fuel pump was stuck. Okay, I need a fuel pump in this thing. So we beat on the fuel pump and still no fuel pressure. And so we keep on going. And we decide, well, we need to look at the circuit. We need the wiring diagram. So this is what we punch up. And I've kind of edited the diagram to fit on our slide here. But it shows you here is your fuel pump relay in the under hood wiring junction block. The fuse is up in that junction block as well. It's a pretty straightforward relay that has the terminals we've been talking about that are all pretty standard. And then the fuel relay, the fuel pump relay is controlled by the computer. See this fuel pump relay control. So here's what happens here. On this particular one is that the computer controlled the power side, not the ground side, which is a little bit unusual, but so it would provide 12 volts up here. That would go through here to ground. Then that would energize the relay. The relay should click over. And now we can have power then flow from this terminal to from that terminal to from this through down to this to power our fuel pump. Now you might be thinking, well, what's the deal with this thing right? I'll make it a different color. What's the deal with this? A fuel pump prime connector on the engine harness next to the battery. What GM did on a lot of their cars is they would actually put like a gray connector here, little pigtail, and they would splice that thing in so you had a little spot where you could jumper power to the fuel pump and bypass the relay, which was kind of a cool deal. It was basically in there for diagnostic purposes. That's what that thing is right there. Okay, so anyways, there's the circuit. What are my common culprits when I have no fuel pressure? Bad fuel pump, bad fuel pump relay, maybe a restricted fuel filter. But usually it's pump and relay. Here is the relay when I take it out. And what I love about this, guys, like we've been talking about, these are our standard relay terminals of 85, 86, right? That's the control circuit. You guys have tested this out multiple times. So that's my coil control circuit. And then that's going to cause it to switch between 87A to 87 and connect 87 over to 30 when the fuel pump's turned on, right? It's pretty standard relay. It looks a little weird because it's the GM one. It's got the small terminals, which kind of stink. They tend to melt over time. But anyways, pretty standard relay. So, you know, what's easy here? Quick and easy. Remember, I've told you guys, hey, just switch relays. So which pin will we need to supply voltage to activate the relay? We would need to provide power right here, right? If we put power right there, the relay should turn on and it should give power to the fuel pump. So let me get rid of that. And pins the bypass relay. We'll get to that. There we go. 87 to 30. So we bypass the relay. Basically, we take a jumper wire and we jump pins 87 to 30, which is exactly what the relay does when the relay turns on. So boom, we did that. And we got our low amps probe around it. This was an old Snap-on one that I was using at the time. And you can see that now I have 56, 57 PSI of fuel pressure. So it tells me, hey, the fuel pump works. And I've bypassed the relay and it's working now. So what do you guys think's going on here? What do you guys think? I know what I would think. I would think bad relay, right? Switch the relays with something else. Some of you guys might have already done that at this point. So this is what it's reading on the thing, which basically says it's pulling 5 amps. Okay. So that's pretty cool. Fuel pump runs, we activate it. So basically, we put a little LED light in place of the control circuit of the relay. And when we cycle the key on, the light turns on. So all this stuff makes it look like, hey, the control side of the relay is working and the switch side's not working. I mean, it really looks like a bad relay, right? But we switched the relay and guess what? No good, no game. Switch the relay with another relay, which, like I said, you guys probably would have already done that at this point. Quite frankly, I did too. But then I kind of went backwards and added some other steps to kind of put together the case study so you can make sure that we covered all of our bases. We put in a new relay and no dice. It still did not have fuel pressure. So now we're going to have to get out our meter and really start to figure out what's going on. So we actually, what we've done here is taken a couple little wires, back probe this thing so it's hooked up and the relay's in there. And now we're doing some voltage readings, back probe with the relay. And what we see here is we're actually measuring a voltage drop of 1.8 volts on the control side of that relay, which is too much. And so what's happening is the relay's not being activated because there's too much voltage drop there to really make the relay function correctly. Now it says, look at the driver circuit. What the heck's a driver circuit? A driver circuit is a circuit in the computer that is there to function something like a relay or a fuel injector. Like your driver circuits control the output devices on our computers. So fuel injectors, evap solenoids, fuel pump relays, they're controlled by transistors, special transistors inside our computer, and that special transistor circuit is called a driver circuit, okay? So we're thinking, oh, maybe I got a bad driver circuit in my computer that is dropping voltage here. And I have to, replace the computer or something, right? What you'd want to do is your next step is to go back to the computer and measure your voltage drop there. So, we have a couple of possibilities here. We either have a voltage drop on this wire, right? Like this wire has some resistance somewhere, or maybe at this connector here, or at this connector here. Or our other option is that we actually have resistance in the driver circuit of the computer, or maybe resistance in the computer ground. Oh no, it can't be a ground connection because this one provided power. So it's either got to be a bad driver circuit in the computer, our resistance is there, or the resistance has to be in the wire. Those are the options we had at that point, okay? So it's a computer or it's a wire is where we were at, right? And you always get a little nervous when you're having to replace computers because computers don't go bad that often. They do go bad, but they don't go bad that often. So now we're back to our service information. We got to look at a pin diagram. We figure out the wire we want is on pin number 3. So we start trying to get to that pin number 3. So what you guys can see right here is we pulled the computer up to get access to it. We got some calipers here kind of pulling the wires out. We're trying to get our meter over here to measure some voltage. And in the process of doing all that, boom, the van started up. And it's like, well, wait a minute, what's going on now? What happened is I moved these wires and stuff around, okay? And this brings up something pretty cool, something that's a good test. And it's actually an old Ford test. When Ford first started doing computer controls, one of their official tests was the wiggle test, the old Ford wiggle test. With the idea is that if I had a bad connection, if I wiggled the wires and I tested it again and now stuff started working, oh, then I just found my problem. So essentially we moved stuff around and we inadvertently did a wiggle test, even though that's not what we were trying to do. But now the van started. And so that tells me that, oh, I don't have a computer issue. I have a bad connection issue, right? I have a bad connection. Remember how I said earlier in our class, I said most of your problems are going to be like components that are defective or bad connections. Okay, so it's not a bad component, it's a bad connection. So from here, what we did, we started moving stuff around again, and now the van died. And we start kind of wiggling and really investigating and looking closely. And this is what we found for pin 3 of the computer, is that the wires just pulled right out of there with not too much force, okay? And you think, oh my goodness, I got to change the wire harness. No, these guys are repairable. It requires special tools. It's kind of a pain in the butt, but you can actually repin these things and put it back together. It's delicate work. It's a pain, but we fixed it and got it running, and that took care of our issue. So, we went down the trail of, looking for current flow, measuring voltage drops, and using a fuel pressure gauge. And you can see that, the meter definitely is used in conjunction with pulling the wiring diagram in a good progressive way of thinking, like problem solving, kind of taking things step by step by step. So hopefully you guys enjoyed that story. Remember that you really want to, oops, I closed that screen too soon. You really want to test dynamically. Don't just test statically, test dynamically. Do voltage drop testing, not just plain old resistance testing with your meters, okay? Try to load the circuit whenever you can to actually flow amps through wires to find those problems, okay? All right, so let's pull this thing back to our class, and let's finish this out and look at where we're at, because it's 7 o'clock. Tonight I'm gonna do our meter class and my scan tool class, and so let's pull this thing back now that we finished that no start case study. So I'm gonna I'm going to change my screen share, and I'm going to go back to the internet. And when I do that, I'm going to close that one out. All right. And so we were looking at that. Here's our class right here. And so if we finish this out for this week, we had to take this little quiz. And really the big activity for this week is one that I'm pretty excited about. And this is the RX-7 charging system diagnosis. Okay. This is where you watch the YouTube video and you follow along with me as we test out the charging system and starting system on our RX-7. And this was one where I initially started making this video to show you like an example car of how it's supposed to work. And in the process, we found that this car had an issue. And so it became kind of a live action case study where I ask you questions like, what is the state of charge of that battery? And get you to answer those questions. And we'll go through here and test the starting system, and then we test the charging system, and we'll ask you some questions like, oh, it's running right now and it's running at 13 volts. Well, what should the battery voltage be when it's running revved up? Okay. So this is why in previous weeks you tested your car. Hopefully your car tested out okay. And you can compare the readings you got last week to what you're getting on this one. Now, what I also have done for you is I wanted to give you a good example car, because answering some of these questions might be kind of tricky if maybe your car tested weird, or you weren't able to test your car, or I don't know. And so here is what I've done. I'm going to go back to our course, and I just finally got this edited and posted. And I'll tell you, it takes a lot more work than you would think it would take to get these videos done. But we are actually all the way down here in week 8 here, right? Next week is spring break. We have next week off. And, oh, it's not letting me see my week 8. So let me do this and fix it. I'll leave my student view. And we'll go back to modules, and we'll make sure that those guys are unlocked for us to see. I don't know if my zoom control was blocking it or what was going on. So we'll make sure that that is clicked and that is clicked. This is clicked. In fact, you know what I'm going to do, guys, is I'm going to make sure that everything is clicked for you guys, so you can watch all the stuff, do all the snap-on meter information, and get all that stuff done. Okay, everything is clicked. Now, if I go to student view, hopefully we should be able to see everything. All right, and we are way down here now. We are on week 8. And what I've done is I've put in a couple things. Overview of week 8, we did the no start diagnosis, but here's a good handout. I think this would be something that you guys would definitely want to download to your computers. In fact, I'm going to click that thing so it will download it, and I can just open it up. And it tells us, it says, hey, if I'm doing voltage drop test. Now remember that a voltage drop test is going to show you where resistance is, right? Voltage drops equal high resistance in our circuits, right? So if I'm voltage drop testing a high current circuit like your starting system or charging system, here's your rules. Most manufacturers will say 1 volt would be the maximum voltage drop you would want. I would prefer for it to be a 1/2 volt or less. A 1/2 volt on the negative side. Again, I would prefer it to be less than that. I want less resistance in my wires. And so what you see on this screen here is we've hooked up our voltmeter here. It's at volts DC, and we're measuring the voltage drop across this charge wire right here. So if there was resistance on this wire, by hooking up our meter like that, we would be able to measure if there is resistance there. And so if I have more than, 1 volt here on my meter, when I'm hooking up that thing and I'm measuring that between the positive battery terminal and the big charge wire coming off the back of my alternator, that would tell me that, whoa, I have resistance on that wire. That's going to affect my alternator's output. On the negative side, I would hook up my meter to do voltage drop on my negative side. I would hook up my meter to the negative battery terminal, and I would hook up the other side of my meter to the case of the alternator. Now, that might seem kind of confusing, right? So here's what else I have done is I just made, if I go back, I just made a video testing a Toyota product on this, and you can play it in this window, or you could go to it straight on YouTube. But I actually do these tests using both the snap-on meter and some cheap meters. And I picked this car because the alternator's right on top. I can get to it pretty easily. It's, pretty straightforward. So there I'm going to that charge wire on the top of the alternator, and I will then go over to the positive battery terminal. So it'll show you how to do it. So basically this video is how a car should test. This is the car that's good. It tests perfectly. The RX-7 is the example of a car that has some issues. So you can watch one video, compare the readings I get on one video to the other video. And when you do that, you should be able to, if I go back to, I'm going to go back to the calendar and back to that assignment. It should make it pretty easy for you to then answer these questions. And how I would do this is I would take the questions and I would copy them. So I'm going to hit Control C, and then I'm going to hit reply. And now I'm going to hit Control V and put the questions in there, and I'll put my answers. So what is the state of charge of the battery? I don't know. Maybe I looked it up and I felt like the battery was at 90%. And I could put that in there. And what I love for you guys to do is like change the color or something so it's easy for me to see your answer. What's the available voltage? Maybe it was at 11 volts. And I will highlight that. And then, did it pass? I'm going to say, yes, passed test. Starter. Okay, right? So anyways, you go through and you start, answering the questions, right? So that's the assignment. I think it's pretty cool. It gets you actually trying, so to speak, doing a diagnosis virtually, so to speak, on a car. That is really your big assignment for this week. I'll submit that thing. And now if I go back to my calendar, you'll see that there's a little line through this thing. Now, there's no homework stuff due next week. Remember, that's spring break. I want you guys to enjoy your break. When you come back from break, though, there is the Horn Diagnostics Part 2. And by then, I should also have the Formula V starting system diagnosis, which will be similar to this one on the RX-7, except this one has an issue with the starter for you guys to diagnose. Basically from there, we're kind of wrapping things up. The big thing that I just opened tonight was all the other weeks. So you can see if I go back to our course, all the different modules. So if you want to get Snap-on certified, remember that's worth 50 points of extra credit for you. So you can start working on that. There's also some activities on CDX. So honestly, at this point, guys, now that we're halfway through the semester, remember, this is only a 1-unit class, so I'm really trying not to kill you. We've covered the majority of the information. I really only will have a few weeks, maybe a couple classes left where we'll do a Zoom session and I'll talk to you and give you some stuff. But the bulk of the information is in Canvas now. It's unlocked. You can get certified on the Snap-on meter. If that's something that you want, those bonus points, you're interested in doing that, and I'll get you guys plugged into to Snap-on here real soon. There's a few other things to kind of finish up. There'll actually will be like a little final exam for you to take on there and just kind of round things up. Remember, the goal with this class is to get you using one of these meters, you know, or any meter, whether it's this one, a Harbor Freight one, or a $400, you know, fluke meter, or the Snap-on 596, is to get you using the meter and kind of doing some stuff and thinking about some stuff. The key thing is, you know, getting a wiring diagram and thinking about how the circuit works. And if you can do that, then you'll save yourself a bunch of time and frustration before you walk over with your meter and just start blindly testing stuff. So my tech tip for you guys tonight is to always, you know, print out that wiring diagram and figure out how the circuit works on paper before you go and try to figure it out on the car. Okay, always figure it out on the paper first, because it's going to be a lot easier to see on the paper. To figure it out on paper, you're going to have to understand how electricity flows, right? Series circuits, parallel circuits. Remember, electricity is always going to take the path of least resistance, and you got to know a little bit about Ohm's law, which I beat you guys up for weeks and weeks. So hopefully you guys have that stuff down. But figure it out on paper, and then it's easy to figure it out on the car. Okay. Questions on any of that stuff, guys? Okay, so if you guys are in AT 181, that's all I had for you tonight. We did that nice little no start diagnostic case study, which hopefully you guys enjoyed. You got to see how you use your meter along with the wiring diagram and just some like common sense stuff as well. We got to demonstrate using some different ways to test circuits, and we looked at low amps probes. So hopefully we get you kind of thinking in this diagnostic mindset. With that, you guys are done. I'm going to do this. I'm going to stop the recording.